Okay, so good morning, everyone. So this is our.
I'll go bring people.
Okay. Okay, so good morning, everyone. So this is our second last seminar series for this semester, and also this is our second in-person seminar for this semester. And today we have Dr. Will Jackson from Department of Earth Sciences, University of Memphis. He is an assistant professor at the department, and he also graduated he did his master's from University of Memphis, Department of Earth Sciences in 2012, and he did his PhD from University of Alabama. And Dr. Jackson is an earth science system scientist who, with a focus on tectonic processes. His research involves more into integration of sedimentology, stratigraphy, and structural geology with geochronology and upper-crustal to understand sediment province and relationship between deformation and deposition. So today, for this seminar, he will be talking about his current work on integrating field-based sedimentology and Zircon uranium geochronology to determine spatiotemporal development of frost belts. And so with that, let's welcome Dr. Jackson in our department seminar and giving our full attention. Okay, over to you.
Thank you. Thanks for having me today. Before I begin, I always like to acknowledge funding sources, of course, but also the labs where we get a lot of the analytical data from. And so the information we'll be looking at today has primarily been produced through the LaserCon Center at the University of Arizona. This is the mass spec that you're seeing there is their multi-collector. But more recently, since I've been at Memphis and even a few years before that, I've been utilizing mass spec at the University of Arkansas. And then moving forward, we're setting up collaborations with UConn, with Dr. Julie Fostick and her helium lab. So to do helium analysis moving forward. I've set today's talk up into kind of 4 components. I'd like to just kind of start with the motivation and the application of taking essentially a field geoscientist that goes out and collects a lot of observations and rock samples, and then combining that with kind of modern day analytical age data. And so we'll work through why I think that's kind of cool and important, and then how we just present the data, especially with clastic sedimentary units. And then from there, I've kind of got to I'll take us on a quick whirlwind experience around the world to look at different orogenic systems. And so these are going to be kind of brief intros to some of those case studies. I wish I could go into more detail, but I think it's best. I wanted to try to present multiple interests of mine to maybe kind of key in or present possible collaborations and ideas for that. So we'll continue looking at orogenic systems in general, but we'll do it from kind of 3 different lenses. We'll start with how do we record the initiation of mountain building? We'll look at the Laramide Belt in the Western US. For that, we'll look at how these systems can record ongoing tectonism in orogenic systems. We'll go to the Tibetan Plateau for that and look at some really cool stuff in East Tibet. And then finally, we'll come back closer to home and look at the Gulf coastal plain and look at actually the full duration of an orogenic system, and that's going to be the Southern Appalachians. So we'll look at how the Gulf coastal plain strata can record that entire orogenic event. Okay. Oh. I'm trying to advance the
down button. No.
There we go. Thank you. So when most people think about tectonic studies of thrust belts, I think our minds initially go to the hinterland regions where we're looking at intermediate, high-grade metamorphic rocks and really nice strain indicators that we can go measure and look at these kind of deeper crustal processes and record of convergent plate boundaries. But where my interests lie is, and I would argue maybe a better record, if we want to look at the full orogenic system, is to kind of shy away from the guts of it and go off to the edges in these foreland basins and foreland thrust belts. Because as the hinterland regions are being exhumed, those rocks are being weathered and eroded. That becomes sediment that gets transported out to the flanks of the orogenic, the high topographic areas, and it gets deposited in the foreland basins. Those foreland basins are then subjected to similar kinematic experiences through folding and faulting. So we can go out into the field and we can investigate the sedimentary rock record. We can look at stratigraphic sequences. We can look at different type of unconformities. Here we've got a nice angular unconformity in some strata. And we can even look at the composition of certain sandstones or conglomerates to tell us about where the material is coming from and then when it was. Okay? And this is not anything new. This has been standard practice for decades now. But when we look at the precision of the spatial and temporal resolution that we have on these foreland systems, there's a lot of work to be done, right? And whenever I kind of realized that as a student, that's when I got really excited, right? We get to still ask these fundamental questions about, hey, when did this mountain belt start? How long did it persist? And maybe how long did it take to destroy it, right? These are basic questions, but they're still kind of at the forefront of us trying to quantify. Okay? This is a great example. These are Pennsylvania strata out in northern New Mexico. They're associated with the ancestral Rocky Mountain orogenic system. But the age for the stratas fairly broad. Usually it's undifferentiated. It's just given Pennsylvania, and it's given this kind of ambiguous age determination because it's a lot of plastic material that lacks really nice index fossils to constrain the biostratigraphic age. And it also lacks, in this case, any type of interbedded volcanic ash layers. Okay. And so where I kind of try to step in is looking at how can we maybe sample, right? We've got this relative age determination well established, right? We know principle of superposition, we've got cross-cutting relationships, and we've got principle of inclusions. Where can we take advantage of those, bring in new modern analytical information to really kind of bracket the timing of events where we see this angular unconformity? This is a delta sequence, right? This is telling us as the delta is being deposited, we have active tectonism in the region. Okay, so these are important kind of processes that we'd like to quantify. The type of data that we'll look at today is zircon, uranium-lead geochronology. Zircon as a mineral is really advantageous to use for a lot of reasons. Primarily though, when it forms, it incorporates a lot of uranium into the crystal lattice. This is hundreds of ppm into thousands of ppm. At the same time, it excludes lead. Okay, so we're talking tens of ppm. This allows us to get really nice, robust parent-daughter isotope ratio determinations. It's also super common in intermediate and felsic igneous rocks, so it's going to precipitate out really as long as you're not in a mafic or ultramafic rock. So it's super common, and then it's also almost impossible to get rid of. It's chemically and mechanically robust, and so it's going to last forever. And we see this in a lot of the studies focus on trying to reconstruct the Hadean now. They're having to utilize 4.1 to 4.4 billion-year-old zircons. So a lot of that information from what we're kind of figuring out about the Hadean is coming from 4 billion plus zircons in the Jack Hills Formation in Western Australia. So these zircons are forming within hundreds of millions of years after Earth formation, and we still haven't been able to destroy them, right? They really like to hang around multiple generations of different plate tectonic processes. From a systematic standpoint, the uranium lead system's really great to use because you have two radioisotope systems to take advantage of. You have uranium-238 and uranium-235. Those are both radioactive. They decay to stable lead products. So 238 will decay to lead-206, while uranium-235 decays to lead-207. So when we measure these radioisotopes in the mass specs, we can collect information on both of these systems, and then we can actually do an internal check on the accuracy of the instrument and our calculation right there in real time. We can see here on the y-axis we have the 238, 206 system. On the x-axis we have 235, 207. And the blue line through the middle of this chart is our Concordia line. This is that kind of one-to-one relationship between the two systems. It's curved because of the difference in decay rates between 238 and 235. So uranium-235 has a half-life of about 700 million years. So it decays pretty rapidly, where the half-life for 238 is 4.5 billion. So that disparity in decay rates creates this kind of curved Concordia line, but this is our one-to-one relationship. And we measure the ratios, we'd expect them to come to the same conclusion, right? To calculate the same age. Because of the abundance of 238 versus 235, we can also calculate a third age. This is lead-206 over lead-207. Okay, so because of the abundance, we have a standard 137.88. Okay, and that gives us the slope. We determine the slope. We can calculate a lead-lead age. Okay? In fact, in most modern mass specs, in most modern age determinations, we're not measuring uranium-235. Just because it's such low abundance, we throw it out the window and we just measure 238, 206, 207. Then we also measure lead-204, mercury-204 to try to calculate and estimate the initial load. The diagram on the right really illustrates the spatial resolution that we're beginning and over the last 10 years to really start to acquire. The bottom figure here is an isolated zircon crystal cathode luminescence image, so we can see these oscillatory bands. And then the individual red kind of rings are individual laser ablation analysis bits. So we do this, we take in situ analyses of the crystals, we blast them with a plasma laser that ejects the system isotopes and then ionizes them through the mass specs. We measure the ratios, and then we can actually map out age domains on individual crystals. That's what the middle diagram here is showing you. This color wheel is related to the ages that are determined from each blast. So you see the big takeaway here is we have older ages in the 90s, almost getting close to 100 MA in the core of the zircon. And as we go out to the edges, it gets younger and younger. And we have a nice, the red band around would be a nice metamorphic rim with ages kind of in the some of them are getting down into the 50s. Okay. That also correlates to concentrations of certain elements. In the top diagram, you're looking at a uranium divided by thorium plot, and we see that same pattern arise. We've got low values in the core associated with the older ages, and then along the rim, we get really high uranium thorium values. That's our kind of key indicator that we have metamorphic overgrowth. So I was telling you, it's really hard to destroy these things. You're looking at an igneous zircon in the core that was then brought to the surface, eroded, deposited, and then buried due to thrusting at the next orogenic event. It goes through regional metamorphism and it grows a rim around it. Okay, so these are huge tectonic processes that are being recorded, and it gives us the ability to really kind of unfold and reconstruct these different events. So let's go through actually a nice little application of that and look at what the data would look like if we dated an igneous rock. Because I've only dated one igneous rock in my life, we'll use that. This is the late Triassic Ganzai Pluton in East Tibet. The Pluton actually crops out over here on the right side of the image, kind of the less subdued, kind of jagged highlands in the background is the Pluton itself. It's intruding middle to late Triassic turbidites, so sedimentary rocks down here in the valley. You can even see some of those sedimentary rocks have been thrusted and folded over here to the left. So they do make some of the high peaks over here on the left side. But we wanted to get a more precise age on the Pluton itself. So we sampled it. We separated out zircons from that bulk rock. And then we analyzed it via laser ablation ICP-MS. What you're looking at is the results of this. This is our now, we're still in our Concordia space. We've got 235, 238 ratios. These green ellipsoids are individual analyses, and the red line is our Concordia line. Okay? And so what we're looking at here is that we got really good analyses. Our results are really robust. They're all overlapping on the Concordia line, so we can kind of reliably trust those results. What the ages actually look like, we plotted up in just basic histograms, right? We have age on the x-axis, and we just bend it up via frequency. The purple curve line is a kernel density estimation curve, and so you can smooth or unsmooth these depending on how what values you put into this. But I've put a bandwidth of 20, and it's resulted in a pretty nice Gaussian curve on our age distribution. And this is really nice. This is what we hope to expect if we were thinking about a magma system cooling and crystallizing, right, and becoming a rock. That's what the zircons are recording. That's the process that they're recording. So we really got excited when we saw that. But the end result is we want to actually be able to say, hey, what's the age, right? And I'll go back for just a second. If we show our frequency, we could pick the peak of the KDE, that's fine. But you can make an argument that maybe we should take the youngest analysis, or maybe we just take the oldest, right? That's when it first started to crystallize out. Here's our last gasp of the zircons forming. There's a question on maybe what or how we should calculate that age. Best practice is to take a weighted mean average. So what we're looking at here is analyses, just end value of analyses. Each vertical green bar is an individual analysis showing you the 2 sigma era of that individual analysis. And then here we have a weighted mean average of all of the analyses together. Okay. That weighted mean average gives us a value of 219 MA, and that's our age for the Pluton, for that granite sample that we collected, right? We get in one individual age that tells us about that process, that cooling and crystallization. That's well and good for intrusive igneous rocks, but when we start thinking about sedimentary systems, we're thinking about completely different processes. Now we have large-scale drainage networks that are eroding material from vast continental expanses. They're transporting that material, they're depositing it along the way, they're picking up and eroding more local, other previously existing sedimentary or metamorphic rocks, and they're ultimately dumping it into a depositional sink, a sedimentary basin. In this instance, it would probably be the delta system off the coast. And so it's amalgamation of a lot of different individual ages, right? It's not just, we're not just going to be able to get just one age from these systems when we data sand or sandstone. We get a spectrum of ages, and that spectrum is much more complicated, but it provides us a lot of insight where we can start to characterize source terrains. We can actually determine the sediment provenance, where all the material is coming from, and we can establish a maximum depositional age for that unit. And that becomes really important if you're talking about coarse-grained clastic material, because you're never really going to have good fossils for those units. There's not going to be a lot of good stratigraphic age features to go off of. So for this, we need to characterize. The main thing we have to think about is how do we actually characterize the spectrum of ages. To do that, it's a statistics end value game. So you want to try to make sure you sample or analyze enough grains per sample. And then after that, we want to represent via just a basic histogram or kernel density estimation plots or probability density plots. Okay? These are, again, KDEs are just going off the frequency of age distribution. The PDPs actually incorporate the error associated with each analysis. I'll be showing you exclusively KDEs for this. This allows us then, once we characterize each sample, we can start comparing it to similar age strata, or we can do it sequences from top to bottom of stratigraphic intervals. Another really important thing and kind of a theme for the rest of this talk is maximum depositional ages. So this is actually taking that youngest age population out of the spectrum, isolating it and treating it just like we just treated the granite. So taking a weighted mean average, establishing a single age and saying, hey, that's the maximum age that this unit could possibly be. It could be anything younger, but it can't be older. And that's fundamentally based in principle of inclusions, right? If these sand units are including these zircons, the youngest age, it has to be younger than that. So what does our data look like for a sandstone? What you're looking at here is the sand interval sitting right on top of the Gansé Pluton. So I showed you the high mountain Pluton in the previous image and we sampled it. We're now on the back side of that. And we have sedimentary rocks non-conformably overlying that granite. Okay. We analyzed 168 grains, so 168 zircons from this one individual sample. And you can see on our Concordia line, there's more spread. There's some analyses that fall off of our Concordia line. And for our world, because we want to try to keep our end values up, there's a little give and take with stuff that falls off Concordia. But we see this large spread of ages from kind of 200 MA all the way back into the late Archaic. Okay, and we see this again. Here it is as a histogram, right? We've got time or age on the x-axis. So here we've got 2.5 billion years. So early Proterozoic rocks, middle Proterozoic, late Proterozoic, and then some really high peaks, high frequency in Cambrian time, and then late Paleozoic. Okay, so we have this spectrum of ages, and think of it as a unique fingerprint, right? This sand, this sediment is giving us a unique fingerprint, not only by the presence of certain ages, but also the proportion and the chemistry, if we want to look at the individual chemistry. That fingerprint helps us to identify where the sediment was coming from, right? Because that mixing of all of these individual peaks is unique in space and time.
So this sandstone layer then cannot be older than 200 something million years. Is that how you use that?
And so if we, here, what I've done is isolated a subpopulation of grains on the youngest peak right here. And I've treated those grains here, we've got 16, and we take a weighted mean average. And that weighted mean average gives us that maximum age for that sandstone unit. This was really important when we were in East Tibet because we were some of the first people that have really gone in and mapped and looked at these units. So there's no age control on them whatsoever. So this is kind of this first order estimate. And the weighted mean average we got was 216. So we were really happy. This makes a lot of sense, right? If it's sitting right on top of that Pluton, unless your sediment source is changing drastically. These are nice alluvial fans, so it should be kind of more localized sediment source to sink systems. And we get a very similar value for our maximum depositional age versus the actual age we got for the Pluton.
So these sandstones are not metamorphosed at all, even not even low degree.
Nope. So let's take that information of how we can take a sandstone, we can date it, we get the spectrum of ages, we get a maximum depositional age. Now let's try to apply that to some different tectonic settings. Okay? The first one we'll look at is the Laramide orogeny. So I got really interested in Laramide for a lot of the same reasons I'm sure a lot of you are interested in the New Madrid seismic zone. And that's because we see this deformation really far away from a plate boundary, right? For the Laramide, it's the easternmost uplifts of our Rocky Mountains in the western US. And it persists from New Mexico, Arizona, all the way up into Montana and South Dakota. It's characterized by these localized basement uplifts. So it's taking the Precambrian metamorphic and igneous rocks, popping them up along with the Paleozoic, Mesozoic, and Cenozoic covers. And they're oriented north-south, northwest, southeast, northeast. Here's an east-west one. So their orientations are kind of chaotic. And they're really far away from the Cretaceous plate boundary, late Cretaceous plate boundary. And so if you're thinking about orogenic systems, this was really interesting to think about because we'd like to think about all the deformation starting at the plate boundaries themselves, especially in convergent margins, and then progressively working their way, the deformation away from that plate margin. But here we see the deformation hundreds, over 1,000 kilometers away from that ancient plate boundary. We can characterize the timing and spatial relationships of Laramide uplifts. They're really this region right over in here. But this chart is just synthesizing, or these charts are synthesizing different data sets that help us understand that relationship. So for all of these diagrams, distance from the plate margin would be down here, is on the x-axis, so 0 to 2,000 kilometers, and then time is on the y-axis. And so time is actually decreasing from about 120 million years down to 20 million years on the y-axis. So time is decreasing, distance is increasing. And so we can look at first order features like magmatic rocks, the youngest marine deposit. So as soon as you go to non-marine, that's kind of telling us that you have exhumation and foreland development, initial Laramide shortening, and then the ending of any noticeable Laramide associated deformation.
What indicates that initiation of shortening?
What's for both of those, it's really just going to be cross-cutting relationships of faults to the either Mesozoic or Cenozoic stratigraphic sequences that they cut. Peter Copeland in 2017 puts all of this together and combines all that data and then proposes a relationship for the easternmost portion of the Farallon plate in regards to the overriding North American plate. And the takeaway here is to follow this gray line. In my mind, we can follow it to about here, and then this is all very questionable. The dashed line could be more dashed and further, but it's important to notice this trend right here. We've got that interaction with the easternmost portion of the Farallon plate to North America, and it's really stable, right? It's stable through the Cretaceous. It's sitting right here. You can envision this being a normal subduction zone, right? Where you've got continued subduction at a similar angle. You've got a lot of magmatism associated with that system. But then right around kind of 90 MA, that trend goes inboard, northeastward into or towards the the North American craton. And it also goes at this nice little shallow angle. And so what's proposed there is that you have this flat slab subduction that initiates with the Farallon plate under the North American plate. One of the ways to explain how we get this flat slab subduction of the Farallon plate is that a younger, hot, thick, buoyant oceanic plateau travels through the Paleo-Pacific on the Farallon plate and then collides with North America and then gets entered into the Trent system. And that entrance into the Trent system is what initiates or drives the flattening of the subduction of the Farallon plate. Okay? So this was proposed in kind of the early 80s, but this was kind of the key paper around 2010 that really is modeling this and showing this conjugate Shatsky rise coming in, hitting the trench, and then influencing via flat slab subduction this kind of northeastward trending zone into North America. In 2018, Gary Axon proposed some more numerical models of this, and y'all could unfold all of this much better than I can. But as I was reading through this, and what I got really excited about was that oceanic plateau is supposed to arrive and enter the trench anywhere from kind of 90 to 85 million years ago. Okay, and if that's what drives the flat slab subduction, flat slab subduction drives the deformation and deposition of the Laramide rock. And so these top four panels are the ones to really hone in on. This is the horizontal devioric stress models. And you've got the normal subduction 90 MA, these two top panels. But by 80 MA, the Farallon plate's gone flat, presumably by the arrival and subduction of the conjugate Shatsky rise. And what that does is put the entire North American overriding plate in a state of compression. That was really interesting to me as I'm reading that, thinking about that, because at the same time, we had been doing a lot of field work in the Laramide orogenic system. We've been working in the northern Bighorn Basin right here on the border between Wyoming and Montana at the Elk Basin Anticline. The Elk Basin Anticline is a fault propagation fold that has a Laramide thrust fault that involves basement directly below it. It's a northwest, southeast trending anticline feature. You see this here today. This is a picture that was kind of taken right here on the anticline, looking northwestward. And so the anticline's breached. It's really nice. We take go camps out there all the time, and this is where they have aha moments of what an anticline is, because they can see the beds dipping to the east over here, and they see the beds dipping to the west over there. You see the bear tooths in the background, the priors are in the background there as well. So you have this classic Laramide structure, and we've been looking at soft sediment deformation features that are late Cretaceous in age. These stars indicate locations of plastic dikes, so really ancient liquefaction features around the anticline. And so I tried to integrate what we've been seeing in the field from a sedimentology standpoint into the way that these numerical models are envisioning this Laramide flat slab subduction. Here are some nice images of some of the classic dikes. You see they're pretty planar in nature. They cut up vertically across the bedding. In all instances, here's a nice kind of sand, silt, coal interbedded interval, and the dike's cutting up through. Here's another one. It's offset by some really nice little normal faults, and it's capped by the overlying sandstone bed there. I always really enjoy working on these and thinking about these, because the first time I was introduced to these type of features is through all the liquefaction features here in the New Madrid seismic zone, right? All the sand blows and different soft sediment deformation that we see here. It's analogous somewhat to the features that we're seeing there. And we were able to reconstruct that. We took the interval that the clastic dikes were in because we assumed that those are the best evidence for paleoseismicity and earthquakes. And we retrodeformed the anticline and the thrust fault to where the interval that has the dikes is horizontal. When we did that, it took all observable basement deformation or offset away from the Laramide thrust fault. And so we interpreted that these clastic dikes are actually recording the initiation of basement offset with the Elk Basin Anticline. When you look at the orientation of the clastic dikes themselves, they have a dominant northeast southwest trend that kind of parallels the regional Laramide layer parallel shortening. And it's actually not orthogonal, but close to it with Laramide joint sets that had previously been recorded by Harry Ingelder in the late 90s. We interpreted this difference in orientation to be that the dikes were forming an unconsolidated sediment. So they're forming at the time that the tectonism is beginning in that region. And so they're actually recording that initial stress build, whereas the Laramide joint sets themselves form post-lithification due to hinge development on the fault propagation fold. So as the fold hinge develops, they actually get extensional joint sets forming kind of parallel to the fold axis. So if we're right there, the thought was, well, let's bracket the timing of these features. We know it's late Cretaceous. All the clastic dikes are within the Eagle Formation. The Eagle Formation is deposited to fluvial depositional environment. Below and above it are shallow marine systems, so deltas and shelf deposits, and you don't get clastic dikes in those. You get different types of features. But the important thing is here we're in this fluvial system. Because of that, the biostratigraphy is not great. Okay. And so all the age constraints for these units are usually based on biostratigraphy of the preceding lower or upper units. And so to bracket the age of the dike development, i.e. the start of Laramide tectonism in the region, we dated the sand source bed, the lowest sand source bed, and then we dated an overlying bentonite unit, the Ardmore bentonite. The age results for that are right here. So here's our sand source bed down on the bottom panel, the bentonites on the top panel. We have age on the x-axis. The green horizontal bars, those are individual analyses that were used to calculate the maximum depositional ages for each unit. And then the shaded region is the plus minus error for those weighted mean averages. We took the uppermost range for the sand source bed and the lowest range value for the bentonite. And so we use that to bracket the timing of the clastic dikes. And that timing was 82 to 78 million years ago. That was pretty interesting to us because it precedes any kind of age range for Laramide initiation in the region, okay, by 5 to 10 million years, depending on which calculations you're looking at. And it temporally kind of coincides, or we think coincides pretty well with this applied inload stress from those models. So if you have the collision of the Chatsky rise and the flattening of the Farallon plate, it creates this inload stress that, according to Axon's model, gets distributed throughout North America within 10 MA. We envision this applied stress load shooting out, affecting or dictating the development of initial Laramide deformation in the region. And then you get flat top subduction, and then this trend kind of takes over. I really like this and been thinking a lot about it recently, because I think there's a lot of work that needs to be done, but it could be a lot of exciting work, because this is kind of a predictive model itself, that if this is correct, we should find similar sedimentological features that are this age in strata from Montana all the way down into Arizona. So we can go out and test this in the field, and we can also set up more localized geodynamic models of this as well.
So in Gary Axon's model, the stress, compression stress generated in the overriding North American plate. So that stress field was set up almost instantaneously, like AdgeNet, the shot ski, the conjugate hits the trench.
That's what I think.
Okay.
Yeah, it's almost like a shockwave.
Okay.
Yeah, that's the kind of strange part of it, but yes.
Because modeling can, I mean, that type of modeling can depend on a lot of things, and depending on the rheology and thermal state, that timing can be kind of adjusted based on our assumptions on the properties of overriding.
So with the last few minutes, we'll skip the application. I tend to do this. I get excited about one. So here we'll look at the Tibetan Plateau. So now we can go and look at sedimentary sequences and detrital zircon from them, and how it actually looks with an ongoing orogenic system. Right? When I got the opportunity to go do field work in Tibet, I jumped on it, because if you want to understand orogenic systems, there's not a better place to go than the highest and biggest mountain or orogenic system in the world. And so we're used to seeing diagrams of this, of India migrating northward over the Cenozoic and then colliding with Eurasia to create the Himalaya and the Tibetan Plateau. Here, the Tibetan Plateau is kind of outlined in red. This is topography. So the red colors here are indicating really kind of elevations 3,000 to kind of a little over 6,000 meters in elevation. I always try to tell people anecdotal way to conceptualize how big the plateau is. And the best way I've come up with is thinking about it from a lower 48 states perspective, that if we took all of the Western US up to kind of the Missouri state border, and we put it in elevation, the average elevation of Pikes Peak in Colorado, that's what we're looking at when we think about the Tibetan Plateau. It's huge, right? It's immense. This is a really nice diagram that I really love to think about and look at, and it's looking at the rate, right? So here we're getting time and then distance, so they get the rate of India migrating northward and colliding with Eurasia. And early on, 70 to 50 MA, we have India really humming along, right, at 100 plus millimeters per year. And then around 50, that decreases to 59 to 80 millimeters per year. And then around 20 million years, it really starts to slow down. Okay? And so there's first order questions of just how do we get orogenic systems this big? How do we get broad plateaus as big as Tibet actually form from a mechanical standpoint? There's a lot of different models to try to explain this. But one thing we started looking at or thinking about is, well, if we want to understand or model the Cenozoic collision of India-Asia, we really need to have a better understanding of these Mesozoic continent-continent collisions that are within the plateau. So we have the Chongtong and then the loss of Lock specifically. There are these microcontinents that also drift off of Gondwana, migrate northward, and collide with Eurasia. And they too are going to develop orogenic systems that are similar to the India-Asia collision, both in kind of space and time. durations. Mike Murphy is at University of Houston. He has this great study that comes out in the late 90s where he's proposing proto-Tibetan Plateau, right? So to explain how large and expansive the modern day plateau is, he proposes that Eurasia was not just a passive margin, regular ocean, land surface, that it indeed was a Andean-like margin prior to India colliding. And so that pre-established orogenic system and smaller, more narrow plateau has thicker crust, hotter, weaker. That's what allows this nice outgrowth of the plateau that we see today. The contrasting models, right, would say, no, it's more of just a traditional passive margin sequence, what we expect to see maybe along the east coast of America. So those two contrasting setups to southern Eurasia will dictate very different outcomes in how the plateau develops. And so one way to understand those systems a little bit better is to look at late Mesozoic and Cenozoic non-marine strata. So the spatial distribution of these are in gray. You'll see that there's been lots of studies in Lhasa, but not so much in Chongtong. And then where we're going to look at is over here in East Tibet, where there hadn't been many studies at all. But look at these non-marine deposits that are terrestrial that get deposited coevally with thrust faults developing in the regions. Okay. Specifically, we're in the Edun terrain. And for our purposes, we can kind of simplify the geology down to 3 units. We've got middle to late Triassic turbidites. These are these light to dark gray, highly deformed units. We have our red beds, our non-marine strata, and then we have our late Triassic Edun arc plutons. So in this map, the green are our plutons, the light gray are our turbidites, and then the brown are our non-marine small sedimentary basins. Notice that the Edun terrain is bound on either side by suture zones. Okay? And the important one here to note is the Gonzaliton suture zone, and it comes along the eastern margin. This is that subduction zone that led to the pluton forming in the volcanic arc system. So this suture zone is active during the late Triassic, early Jurassic, and then shuts off, but since then has been a locus of deformation as these microcontinents continue to glide to the southern margin of Eurasia. It acts as preferential zone of weakness where you get a lot of deformation.
Actually, I'm interested about the Sichuan Basin.
Mm-hmm.
I'm sorry, maybe that's not part of your talk, but is that like, is that a map view or is that section?
Right here.
Right, so that's like, it's like a mechanical block.
Yeah, similar to Colorado Plateau.
Right, and you have the Longmen-Shan Range. You have this big thrust that got the 2008 Sichuan earthquake. So what's the reason to have the Sichuan Basin over there? Like how that was formed? Can you tell me something more about that? Or
Sure. The Sichuan Basin forms. It's got paleozoic. Its thick stratigraphic sequences are Mesozoic and then into the Cenozoic, but mainly Mesozoic. So it's acting as a depositional sink in the late Mesozoic, and then during the Cenozoic, during the India-Asia collision, it acts as an intact, stronger lithospheric block that deformation kind of oozes out around on all. So that's why where you see this rotation and translation to the southeast with the plateau, you also see deformation trend to the northeast of it. And so it kind of acts as this rigid block.
so that's all because of the Sichuan Basin.
Yes.
So if you haven't have that there, you will not have all the strike slip faults and the.
Correct. Yeah, the thought is that you would have just this more systematic expanse of deformation. It also has to do with the syntax of India, right? So you also have the corner coming in of India and stuff being not only rotated, but translated down into Indochina. But yeah, I think from a topographic standpoint, if that's your question, yes, the reason why we see such drastic, we go from the high, fairly level plateau, and we see this kind of drastic topographic drop off down into the Sichuan Basin is because of that block right there. You see a gradual decrease in elevation if you follow a topographic line down to the southwest.
So the basin is stronger
Yes.
beneath, right?
Yeah.
Thank you.
Sure. So we looked at the non-marine strata. They're alluvial fan deposits. We can break them up into kind of three basic units. That's a conglomerate coarse grain unit at the bottom, interbedded sands and silts in the middle. That's what we're looking at here. And then more muds, even potentially interpreted some lake deposition in the upper unit. Here's our field assistant, Xing. He's a new assistant professor in China that we're trying to set up a bunch of collaborations with as well. We also found some of that unit 1 and unit 2 from the Mula Basin in the Suture zone itself. So this was really exciting. It's not very thick, maybe 40 meters thick at most, but it's actually within the Ganze Litang Suture zone, and it's fault bounded. And so we said, hey, if we go in and we date this, we can get maximum depositional ages, and we can bracket the maximum time that this late Triassic Suture zone was reactivated. Okay? And then it got even more exciting because within the Suture zone, they have neogene strata that's sitting there undeformed, nice horizontal units. And so then that's our lower bracket, right? That's always our problem when we get these maximum depositional ages. We've only bracketed one side of it. But here our undeformed neogene provided that lower limit. So we could really constrain the age of reactivation along the Suture zone itself. And so what we saw was at the Mula Basin, we get that, and here we're just probably bracketing the initiation of the thrust faults that are bounding within the units themselves. We got a maximum depositional age of 45 MA, and then we get a maximum depositional age of 41.5 MA. And so when you couple that with the neogene strata that's undeformed, we've really bracketed that reactivation of that suture to the Oligocene. And that was really exciting because that correlates well to thermal chronology in the Longmen-Shan and these numerical models of how deformation has outgrowth on the eastern margin of the Tibetan Plateau. I am going to cut myself off so I don't hold y'all any longer. I can stay and chat about more stuff or the next studies and stuff like that. But I hope that you've at least kind of seen the ability for us to couple a bunch of field data with the new kind of more modern analytical techniques. I will end on maybe this slide is we're taking that to the next level and trying to get helium ages because they're not crystallization ages, they're actually temperature ages. And so we can then track the zircons as they get exhumed through the crust. So we can get multiple ages. We could get a uranium lead age and then follow that up with a helium age and actually track the exhumation as they're being presumably moved up via faulting. I'll take any questions and I'll hang around and chat.
It's more like a query. So when there are some papers that mention there are multiple small continents that are colliding with the northern Eurasian plate. So where does that colliding block went? So when they collide, so it is considered as vertical plateau. So there should be some microcontinent. So are there any human traces of the continent?
Sure. I don't have a map on the presentation where I can help point you to that. but if we reconstruct the paleo position of all these, what you'd want to do is just kind of unrotate these suture zones a little bit to have them trending more east-west, probably not completely east-west, but in a more east-west direction. And so the kind of textbook example of that people are working on trying to correlate would be the Chongtong correlates down towards Indochina to the Longping block. And so that's the one I've really focused on. I think that's most of the information for that rotation and translation is tied to those two blocks. Because there's evidence that maybe there's some type of tectonic fabric that separates them, makes them distinct, but they seem to be from a sedimentary basin development, coherent or at least coeval blocks that are experiencing similar tectonic. That would be presumably associated with the loss of block coming in and colliding.
Can you make some comments?
Sure.
Yeah, please.
The laser ablation is superior to ion beam. I mean, when the first shrimp came, it used ion beam. That's my understanding.
Sure. So the three ways we could do this is thermal, so TEMS, and then shrimp or SIMS, and then laser ablation. And so there's trade-off, there's benefits and downfalls to both. TEMS is going to give you the most precise age. So you can get down to 0.1% precision on individual analyses. The problem there is it's time intensive. So you actually have to dissolve the whole zircon crystal, send it through a bunch of geochemical steps, and then you heat it up and evaporate it off. And so you're also destroying the whole grain as well. And so you're looking at the analogy I always used is when we were doing some garnet age dating. It took us 6 months to get 12 ages. And so to accumulate data sets with n values in the hundreds, you're looking at years. SIMS is actually better spatial resolution, and it is. I've really enjoyed some of the SIMS data sets because you can also manipulate the angle, and you can actually kind of shave off the different layers in the crystals themselves. And so you get better spatial resolution with SIMS, but it's much more expensive. And so, and it also is more time consuming. It's actually more time consuming when you're on the mass spec. So each individual analysis for laser ablation, you're looking at 15 seconds. For SIMS, you're looking at 10 minutes or so per analysis. Don't quote me on that. It's a significantly longer amount of time. And because of that, it's more expensive. What I really like about laser ablation ICP-MS is it's mainly, at this point, the main holdback is just software development. And so because of that, it's advancing yearly. It's becoming, I remember when I first started doing lab runs in 2013, we could collect maybe 600 to 700 ages a day. And now we're collecting 3,000 a day if we run all day. And so just in the last few years, the software, we can remote log in now. So I can send my samples in and remote log into their computer systems and go ahead and blast away. I used to have to, when I first started, I'd have to record the data on a padded notebook paper and stuff like that. I'm passing around different samples where you can actually see the zircon grains themselves, what the mounts actually look like. And so just to give you kind of a scale of what we're working on, the laser beam itself, you can manipulate that really down to kind of 5 microns up to about 30. Usually we set it, the diameter of the laser at 20 microns. And so those are two different approaches to actually ablating or analyzing the grains themselves. The smaller black puck is we actually put the zircons in epoxy, and then you buff off, you cut them in half, you expose the core. The clear mounts that are coming around, we just took the grains and threw them on some 3M tape and went to town. And there's advantages and disadvantages of that. What we were trying to do when we threw them on the clear mounts is actually drill down. When you buff them and expose the core, you risk deleting any of those rims. And so because the software programs are getting better now, we can drill down and we can actually split out the runs. So if it's a 15-second run, we can split it 7 and 8 seconds, and we can capture 2 ages. We can see the rim and the core in one analysis. And so that's why we've gone to just mounting them directly to tape. So.
Even you guess why the flat flux will lead to this strange orientations of the fault in there? Did you find it out before?
I'm throwing stuff on the wall to see if it sticks. But in that paper, it was pre-existing weaknesses, specifically probably some type of ancient normal fault, right? And so right when the oceanic plateau hits the trench, it creates that inload stress. Yeah, it's this really instant inward movement of the stress, and it pops off any zone of weakness in that kind of avenue. What I don't like about that is that you would think it would have to be perpendicular to the stress direction, right? Or those would be the ones popping off.
There should still be some towards direction.
Yeah, but what I try to envision it almost like a car wreck, or when you see in the movies the car wrecks where they two collide and they slow it down and you can see the waves propagating through, and then it comes back to real time and you see all the real deformation. That this is just it kickstarts everything and maybe loosens up some of these pre-existing faults that are zones of weakness, and then the Shatsky rise can get in, and then it's the normal story that everybody talks about with flat slab and the progression of deformation and stuff like that. But I don't want to say that this is controlling a new temporal resolution on the whole orogenic system. This would just be a temporary initial deformation phase to that system.
Yeah, I'm just curious now, what could be the reason behind like those multiples with the zone?
The what?
Yeah, we have multiples with the zone there, the Sanko and the other Bangor. So what could be the reason behind the multiple?
Those are just showing us the progressions that the plateau itself, especially the interior portions of it, are an amalgamation of multiple episodes of continent-continent collision. So they're delineating these previous collision episodes or orogenic systems. But what I think was really interesting about it, when I think about especially like the surface of the plateau, is that they seem to continue to host most of the deformation within the plateau. So whenever the next younger episode collides, that stress and strain gets focused along those pre-existing suture zones. And we see that with the sedimentary basins, and so they tend to spatially be aligned with the suture zones themselves. And there's just a lack of deformation, or that timing of deformation in the middle of those points.
Then those suture zone must be from the different ages.
Yes. Yeah, you can think of them as getting, this is late Triassic, this is Cretaceous, and then this is Cenozoic, early Cenozoic. So they're younger towards the south.
You have been there, so did you encounter any
real suture zone on the surface?
The real suture zones along the side. So when we go do our field work, we actually fly into Chengdu in the Sichuan Basin, and we get in with a travel agency there with a driver, and we drive up the eastern margin. So we'll drive from Chengdu up to Ganzi, and that's kind of our home base there.
When's the last time you traveled to Chengdu?
2015, and so when I got here, so the helium data and efforts moving forward, it was an NSF grant I got in 2018. Well, I submitted in 2018, and that was really going to be the focus of everything I did was, and then the pandemics kind of put a.
I was more curious, when you go to Chengdu in 2015, did you see anything left over from the earthquake?
So I was there. So the 2013 earthquake.
I was talking about 2008.
No, I didn't see any yet. But as soon as we left Chengdu, we
There is crystals. Actually, there is a site. There is a memorial site where a whole town left in the destroyed state. I was in Chengdu for a month to the place.
Okay.
So it's a bit rough, but yeah, I mean it's really interesting from an engineering point of view.
The first trip, so I'd never really left the southeast before, and that was one of the reasons why I wanted to go do this dissertation. Was I saw it as an opportunity to go actually see the world and go travel internationally. And we get over there. Our first field season was 2013, and the original grant was to do a traverse through the whole Chongpeng terrain to do cross sections and structural geology. And at the time, there's a lot of political unrest between the Tibetan monks and the Chinese government. And it was the periods 2012 to a lot of them were putting themselves on fire.
Oh, wow.
And the town that they were doing that was supposed to be our home base. And so our permits got taken away. And so we kind of had to, on the fly, come up with a new dissertation topic, which was interesting to do being there, because one of my advisors thought if we just went there in person to the border, they'd let us in, and they didn't. So we're driving around and looking at those red beds, and all of that came from that. But it was we flew into we fly into Beijing and then fly from Beijing to Chengdu. And that next morning, I woke up and the hotel we were in started shaking. I said, well, what's going on? And our translator, Faye, goes, Will, it's an earthquake. We need to get out of here. Because I jumped up to the window. I was like, it's an earthquake. I was really excited to experience one. And so we ran out into the parking lot, and we were all kind of high-fiving. We'd gotten to experience this cool earthquake. But then we quickly looked around, and it was scaring everybody else to death, right?
So what was the epicenter of that? The 2000?
It was, so the epicenter was, I can't remember the town that they named it after, but it was about 60 kilometers to the southwest. But it was a 7.1
of Chengdu.
Yep.
Right. So that was in the basin.
Yep.
No.
Yep. It was just down here is a small.
Okay. So it's like a frontal thrust
Yep.
or something.
Yep. Yeah. So that was, but I remember, again, this is my first time to ever travel internationally. Second night in China, I said, what have I got myself into?
That's a great thing.
Yeah, it was awesome.
Steve had a question.
You mentioned Southern Appalachians and coastal plain. That's Birmingham, Alabama, or something like that.
Sure.
And what are you doing?
That's where, especially over the last 3 years, a lot of my efforts have been. I worked for the Alabama Survey for a few years after, as I was finishing up grad school. And so they had us mapping in the Valley and Ridge. But I got really frustrated with thinking about going through and sampling, getting all of this data set, a modern Zircon data set, especially for the Inner Piedmont and Blue Ridge. And some of the in situ studies were really having troubles getting zircons out of the rocks in general. And so we just came up with the idea that, hey, let's go and sample the late Cretaceous Ripley unit, it seems like these Cretaceous units actually have an Appalachian signature that could record the entire orogenic system. And so this is the zircon, that uranium lead ages. But here, if you remember that heat map I showed you on the second slide, I've isolated the metamorphic zircons. So I took, these are all from the sand, but I took the ones with the chemical signature for metamorphism and plotted them up here. And it looks like we've got this really nice record that doesn't match the uranium lead ages very well. But I think what we're doing is seeing peaks in metamorphism. It's telling us these major phases of Southern Appalachian deformation. We correlated these two youngest peaks, so the Acadian and then the one that's Neo-Acadian or Alleghanian, however you want to call it. These line up perfectly temporally to garnet growth in the Southern Appalachians. So that's one thing we're working on right now. Is I've had to bring in a bunch of petrologists because we're trying to figure out the systematics of metamorphic zircon growth alongside garnet growth during these regional metamorphic pulses.
So, I guess I'm having a little bit of difficulty with kind of like provenance for Cretaceous sediment, in that they don't actually kind of come down from they're how do I say this? They're ocean, more or less coastal. They're coastal plain, so they're actually from various places that they.
So what we're looking at here are the rocks we are looking at are the red dots. Late Cretaceous Ripley. So this is Maastrichtian, so 71 MA. You've got kind of early Cretaceous. This is the Tuscaloosa group. So this is the oldest clastic unit along the coastal plain. And then here we've got Eocene. Okay, so those that are, and then here we've got the blue is Maastrichtian and the green is Maastrichtian. So same age as the red dot. So all those other colors besides the red had previously been dated. And if you look here, the KDEs for those, every single one of them has a really small appellation, that's that gray bar, has small appellation, and then it has a huge Grenville signature. One of my colleagues and idols is Bill Thomas, and he has a good joke that if you get a Grenville age zircon, all that tells you is that you're on Earth. It's about the extent that it tells you. And the reason why is here's his Appalachian signature curve. It's a composite of a lot of his work. You have big, huge Grenville. You have some older stuff and some unique Wyoming peaks, and then a smaller Appalachian peak. And yes, so then the thought with that is that the sediment is coming from regional to continental scale systems and actually getting dumped in towards the northern portions of the embayment. And then kind of coming down in these delta systems and stuff like that. But what we noticed with our red units right here in our samples is that the age proportions are opposite, it's flipped. We have dominant Appalachian and then a smaller Grenville. And then when we looked at the percent abundance of metamorphic zircons, it was overwhelming. And there's a spatial relationship to this. So this sample right here is the one that's stratigraphically overlying. You know, if we project the Appalachians, they'll continue down here. So as we move from the southeast towards the northwest, you actually reduce the amount of metamorphic zircons in the system. And so we put that whole story together and then did some multi-dimensional scaling to say that the actual main provenance for the Ripley is the Piedmont. So it's a regional drainage system that's eroding the mountain belt, bringing it down to the coast. And then you have this alongshore current that actually moves northwestward.
So it's flowed down the east coast from to the southeast, and then it turns around and goes back up I mean,
Regionally.
Piedmont is actually east of the core of the Appalachian.
Sure. In today's, topographic expression, sure. But these, and we've got that, that's probably during the Cretaceous, since there's still probably a topographic barrier between the actual foreland, and then here's the foreland thrust belt. It probably does, the headwaters probably are derived from both systems in there. But yes, we're saying on that eastern side of the Valley and Ridge, right? So we've got the Blue Ridge and the Inner Piedmont. These are the actual primary sediment sources for the Ripley at that time. And yes, it comes down into the Cretaceous Seaway and has a longshore drift towards the northwest. And so I didn't believe this at first. So I had a grad student, Caitlin, and she's a marine science background. And so she got into dating Gulf modern day coastal deposits. And so she's seeing that exact same kind of signature from Apalachicola River all the way to the Mississippi. And so, and then she dated the barrier islands and the beaches between those, and then the Mobile River. So, and she's done a lot of really cool statistical, so the rivers are inputs, and then the beaches and barrier islands are outputs. And so she's done a lot of sediment mixing models and stuff like that. But she kind of sees a similar trend in, here's Okaloosa, Apalachicola Beach, and Apalachicola River. You're dominated by the Appalachians, and you have a smaller Grenville Peak. And if we look at the Apalachicola River drainage network, it's tapping into that metamorphic and igneous rocks of the Southern Appalachians.
Sometime when we sit down, I'll ask you why you don't see the watch. Or do you?
Oh, so
Not right now.
not right now, but this is our, that was a question we've been working on and asking. I have a PhD student, Maddie, who I think she's the first one to ever really find what I'm going to say is the Ouachita signature. We always just thought they were so similar we couldn't tease them out. But I think she's got her age KDEs are quite different. And she was dating the Hartsville Sandstone in Northwest Alabama. It's interesting. Yeah. I'd love to sit down and show you. Yeah, but that's a huge question for us: is what is the Ouachitas? But we've tried to start to tease that out in this recent paper in Geosphere. So I'm sorry, I shouldn't have ran over time. I should have tried to get to all these.
All right.
Thank you. Yeah, that's same line. So if you want to check with him, you can ask him, take his time and check and see the work. Thank you so much. Thank you so much for joining that work.